Today, network engineers operate entirely through software. They deploy code, and complex architectures spin up globally without a single cable being plugged in. This layer of abstraction provides immense efficiency, but it obscures the physical reality of how data actually moves and processes beneath those interfaces. To truly comprehend modern cloud infrastructure, we have to look past the dashboards and map the historical hardware it replaced. We can trace this evolution by examining the continuous 50-year career record of a single IT architect, Clem Lundie. His timeline stretches from 1970s military radar to teaching Azure and AI in 2024. Notice this 1983 Air Force training record for high-value soldering. He repaired logic boards by hand. Today, engineers achieve identical results using automated scripts. This timeline provides a step-by-step map of the IT industry's ascent of the OSI model stack. In the late 1970s, networking was a physical, component-level engineering problem, constrained to Layer 1 and Layer 2 of the OSI stack. During his time in the Air Force Space Command, Lundie served as an electronic computer and switching systems technician. Engineers didn't write code to dictate logic gates. They maintained the logic through direct physical intervention, troubleshooting and overhauling high-speed circuitry at the board level. A major project of the era was updating how radar data was transmitted. This meant replacing traditional wire cables with fiber optics. Translating radar signals into light pulses over these fibers formed the physical bedrock that modern high-bandwidth networking relies on. The era also demanded extreme physical security. Cryptographic equipment required strict environmental controls, including installation inside Faraday cages to block electromagnetic interference. These military practices for data transmission and disaster recovery established the baseline protocols that would eventually scale into the civilian sector. Early networking required the manual manipulation of electrons. Because it was physical, the system state was highly observable. By the 1990s, the primary engineering bottleneck moved up the stack to layers 3 and 4. Physical hardware became commoditized and standardized. The need to solder custom circuit boards disappeared, replaced by commercial off-the-shelf components. With standardized hardware, corporate networks exploded in size, creating an urgent need for directory services to organize the machines. Lundie managed early enterprise implementations, deploying Novell NetWare production servers to coordinate over 1,000 nodes across campuses in San Jose and Temecula. This centralized directory structure created a new layer of control, organizing machines logically rather than relying on how they were physically wired. In the mid-90s, this internal logic expanded outward into corporate internet implementations and wide area networks. The primary skill set shifted to configuring physical network switches and routers to direct traffic across these larger spans. Engineers now dealt with abstract complexities, managing IP routing tables and establishing virtual private networks to connect disparate geographic locations. As hardware became uniform and reliable, the complexity of networking migrated into the routing logic and directory structures. Moving into the modern era, the physical layer disappears entirely from the network engineer's daily view. This is the result of virtualization, recreating physical switches, physical routers, and massive physical servers entirely as software code. Hypervisors like VMware and Microsoft Hyper-V executed this transition, decoupling the operating system from the physical machine it runs on. This abstraction enabled the modern cloud environment, allowing platforms like Azure to host thousands of isolated systems on shared physical infrastructure. The curriculum Lundie teaches today reflects this shift. Hardware maintenance is gone, replaced by cloud administration and software languages. Managing networks now requires fluency and an array of tools, including Python, SQL, and AI copilots. The engineer's role has inverted. They no longer install servers. They write scripts that command the cloud to provision virtual servers autonomously. These virtualized networks can dynamically scale their capacity and reroute their own connections without a human touching a physical cable. The modern cloud is essentially a software emulation of the physical network topologies built decades prior. The cloud is the automated culmination of 50 years of physical switching logic. This is the OSI model. A first principles understanding of physical transmission accelerates comprehension of abstracted systems. Tracing the logic upward, rules governing physical routing translated into software routing algorithms. Early directory services evolved into the identity and access systems governing the cloud today. Contrast a modern engineer who only knows cloud interfaces with an architect who understands physical node failure. When the abstraction breaks, the interface offers no answers. Understanding raw fiber optic transmission protocols provides a superior mental model for debugging a failing virtual machine peering issue. IT history is defined by abstraction, the process of hiding complexity behind increasingly friendly interfaces. Legacy protocols reveal the rules the software is forced to follow. To master the software-defined future, we must understand the soldered past. True architectural mastery requires seeing through the abstraction to the bedrock logic operating underneath. In the 1970s, military computer networks occupied entire buildings, requiring intense manual operation and the highest levels of classification to function. This was the starting point for Clem Lundie. Working as an electronics and switching systems technician for the United States Air Force Space Command, his daily operations involved managing the physical components of these enormous machines. The hardware under his supervision was built for the highest stakes. He served as a lead computer repairman for mobile forward air traffic control centers, keeping complex 3D radar systems operational in the field. At the Air Force Cryptologic Support Center, his responsibilities included servicing over 10,000 cryptographic equipment line items to maintain the network's security. Lundie drove technical progress by developing the protocols required to replace traditional wire-cable radar transmissions with high-speed fiber optics. As a threat assessment officer, he installed Faraday cages, specialized shielding enclosures designed to block electromagnetic fields. This ensured that internal data signals remained pristine, while external interference bounced right off the exterior. Managing systems in this era required a profound hands-on mastery of physical engineering before a single line of software could communicate. By the early 90s, computing was migrating outward. The tightly guarded mainframes of the military gave way to the rapidly expanding commercial tech sector in California. Lundie took his hardware expertise into the private sector. Working as a network engineer for early pioneers like PeopleSoft and Eli Lilly subsidiaries, he managed sprawling corporate campuses with over 1,200 individual nodes. These environments were heterogeneous. IT management challenges were Apple Macintoshes, Dell PCs, Unix workstations, and Novell NetWare servers all had to communicate on the same network. As a project leader, his mandate was to integrate these isolated local networks into the early corporate internet. He achieved this by installing and configuring the Cisco routers and switches that linked these systems into a unified web. Effective information systems management in the 90s meant bridging incompatible systems to create a functioning corporate infrastructure. With the networks connected, the focus shifted to the data they carried. As an IT supervisor for the Pfizer subsidiary Sugen, Lundie managed complex database operations. Supporting biology and finance divisions required constant server performance monitoring, VPN management, and disaster recovery protocols to protect sensitive clinical data. He later applied these enterprise protocols to a different high-pressure environment, the San Francisco 49ers. Working for the franchise's IT department, he provided desktop support and managed the data systems for the National Football League's Player Participation Program. Whether supporting clinical trials or professional football logistics, the core mandate of an information systems manager is uninterrupted operational uptime. Today, much of that physical infrastructure has been abstracted away into a cloud environment, changing the skills required for the next generation of engineers. Lundie transitioned into education to address this shift. At San Jose City College, he serves as a tenured instructor, chairman of the Computer Information System Department, and director of the PC Hardware Lab. His curriculum covers the history of computing, from legacy programming languages to modern virtual infrastructure using VMware and Microsoft Azure. He continues to integrate new tools into the Workforce Development Division, specifically teaching Microsoft Copilot and AI applications. By architecting the curriculum for the Workforce Development Division, Lundie translates his decades of engineering experience into the training standards for the modern workforce. The strength of this educational infrastructure was tested during the COVID-19 epidemic, which required an immediate move away from physical classrooms. Using his expertise in learning management systems like Blackboard and Canvas, Lundie designed the college's emergency modality change strategy. He led the transition of thousands of students from in-person instruction to remote distance education via Zoom and Microsoft Teams. This institutional pivot relied on the same engineering principles Lundie used to scale military networks, proving that remote educational systems required disciplined technical management to succeed. Clem Lundie's 50-year career demonstrates that the most effective way to lead through the future of technology is to have built its foundation with your own hands.